Hello everyone. Many of us have gone swimming at one point, and while swimming, we have gone underwater and opened our eyes to find out how everything looks underwater. Underwater, everything looks slightly distorted. Like you might have seen your friend standing at the edge of the water while you were underwater and realized your friend suddenly looks taller. When you look at them from above the water, their height looks normal, but from under the water, they look taller. What is happening here? Well, the reason is refraction. Stick around till the end of the video to understand how this works. But first, we need to talk about light and light rays. When you shine a torch, you can see that the light rays always travel in straight lines even when they get reflected. They travel in straight lines after reflection. But sometimes when the light goes from one material to another, it bends and starts moving in a new direction. This bending of light is called refraction. Now you may be asking, but why is light bending? It's because of the speed of light. Let me explain. Light has different speeds in different mediums. For example, the speed of light in air is more than the speed of light in glass. But this still does not explain why the light bends the way it does. Well, for that, we need to look at waves of light. In one beam of light, there are multiple waves of light which can be hard to keep a track of. So physicists figured out a way of looking at how multiple waves are moving. This is a wavefront. It's essentially an imaginary plane which represents where the waves are at any given point of time. So if this is a source of light and the waves are parallel to each other, then the wavefront is just a plane perpendicular to the direction of the motion of the waves and is situated at the place till where the waves have reached. You can see that the wavefront moves forward at the speed of light. So how does this concept help us? Well, because we know that light slows down when it goes from air to glass, the wavefront must also slow down. Now, if the light is entering the glass at an angle, one part of the wavefront will reach the glass and slow down, while the other will be moving at the same speed as before. This is what causes changing of direction. Because to keep the wavefront intact, the light has to bend, as you can see on the screen. We can see that reflection essentially depends upon the speed of light in a material. This is an important concept. So important, in fact, that we have a word to describe the speed of light in a material when compared to the speed of light in vacuum. It's called refractive index. Absolute refractive index of a medium is defined to be the ratio of the speed of light in vacuum to the speed of light in the medium. Similarly, the refractive index of medium 2 with respect to medium 1 is the ratio of the speed of light in the medium 1 to the speed of the light in medium 2. The speed of light in water is 2.25 into 10 raised to 8 meter per second, or around 2,25,000 kilometers per second. And the speed of light in vacuum is 3 into 10 raised to 8 meter per second, or 3 lakhs kilometers per second. Thus, the refractive index of water with respect to vacuum is 1.33. Here are some materials and their refractive indices with respect to vacuum. Now that we know this, we can look properly at refraction and the laws of refraction. Look at this diagram of refraction. Here we have an incident ray, a refracted ray, and a normal. This brings us to the first law of refraction. The incident ray, the refracted ray, and the normal all lie in the same plane. You can see this just by looking at the diagram. Going back to the diagram, this angle is called as the angle of incidence, and this angle is called as the angle of refraction. This brings us to the second law of refraction, also known as Snell's law. For any two media and a wavelength of a light, the ratio of sine of the angle of incidence and the sine of the angle of refraction is a constant. This constant is the refractive index of medium 2 with respect to medium 1. To find how the angle of refraction changes with the refractive index, let's do a little bit of math. From Snell's law, we know Now if we take the sine of the angle of refraction to the other side, we get this. Now if the refractive index was 1, then the angle of refraction is just the angle of incidence. If refractive index is greater than 1, then the angle of refraction becomes lesser than the angle of incidence. This means in the ray diagram, it looks like the light ray has bended towards the normal. For example, when the light goes from air to water. If the refractive index is less than 1, then the angle of refraction becomes more than the angle of incidence. This means in the ray diagram, it looks like the light ray has bended away from the normal. For example, when light goes from water to air. Now that we know all this, we can finally understand why our friend looks taller when viewed from underwater. If you look at this diagram, this is you underwater and this is your friend standing up. If we take one ray coming from the head of your friend, it will reach the water at some angle, but the refractive index of water with respect to air is 1.33, which is greater than 1. Thus, the light will bend towards the normal and reach your eyes. Thus, to you, it will seem like the light is coming from this point. Thus, your friend will seem taller than they really are. Now you know something that you didn't know before. To completely understand what we have learned today, let's look at this problem. Light is incident on a medium with refractive index √3 at an angle of incidence 60 degrees. Find the angle of refraction and speed of light in the medium. Value of √3 is 1.73. Speed of light in the vacuum is 3 × 10⁸ meter per second. Let's look at the first part and find the angle of refraction. We know from Snell's law the ratio of the sine of angle of incidence to the angle of refraction is equal to the refractive index. So, to find the angle of refraction, we just switch it with the refractive index in the formula. Now sine 60 is √3/2 and the refractive index is √3. These two cancel to give 1/2. This is equal to sine 30. Thus the angle of refraction is 30 degrees. Now to find the speed of light in the medium, we use the definition of refractive index. Thus, using the formula, we can find the speed of light in the medium. Now we can write 3 as √3 × √3 and cancel one √3 out, and thus speed of light in the medium is √3 × 10⁸ or 1.73 × 10⁸ meter per second. I encourage you to do more such problems to get a real understanding of these concepts. Let's look at what we have learned today. If you have liked this video, please hit the like button. And if you have any queries, do comment down. Also, don't forget to subscribe to our channel. Last but not the least, don't forget to press the bell icon to never miss another update from Letstute. Till then, keep watching, keep learning, and follow your curiosity. Thank you.